Next, we will find, we will actually plot this function. That's the actual assignment, not the solution. But we plot this function and use the graph to figure out where like if we assume that this is f prime, right? This is not f of x, this is f prime, and we use it to figure out where f is increasing or decreasing. Well, f is increasing wherever f prime is positive. So if this is f prime, it's positive here to the left of 0. It's positive here to the right of 1. And therefore, it is increasing on the interval, apparently, from negative infinity to 0, union. So hopefully this interval notation is familiar from high school. So I'm unioning the interval from negative infinity to 0 together with the interval from 1 to infinity. And it is correct to use exclusive, like curved parentheses, because it is not increasing precisely at 0. That's where, in fact, the derivative is equal to 0, and it's neither increasing nor decreasing. It's just, so to speak, kind of flatlining right there, going horizontal. Likewise, we do not include the point 1, and therefore use the curved parenthesis rather than a square bracket, because, again, the derivative is 0, not positive, so it's not increasing at that point. So there you go. This is the solution to the question. Next, we will find the derivative of the cube root of x. And this is a hard one. This took me a while to really work out all the kinks, but I'll go ahead and print the answer just so we know what we should expect. And the answer is 1 over 3x to the 2/3. So let's see the proof somewhere where I was able to print it in a little bit nicer script in LaTeX over here. So this is f of x, this is f of x minus h, and I take the difference divided by h. Okay. Now, this is where I use that fact that I mentioned quite a while ago when talking about limits, that you can use the factorization of perfect cubes in this example. And if you just kind of maybe call this, it's sort of like this is x and this is y in the difference of cubes formula. Maybe I can even try to draw that with the mouse, although that always comes out kind of awkward and hard to read, but maybe I'll just do my best. So recall that the difference of cubes says that if you have a perfect cube here and a perfect cube here, that this is equal to x minus y, the underlying thing, times x squared plus xy plus y squared. So this is the factorization of perfect cubes. And the idea is I would like to get the cube of each one of these individually, which is what I have on the left-hand side of the formula. So I would like to basically throw into the formula, instead of x, have x to the 1/3, instead of y, have x minus h to the 1/3 thrown in for y. And then I just throw everything into here consistently. And what you see is that you'll have, this will turn into, after throwing in all those substitutions, this you can identify with that. And it shows you that if you want to cube the individual pieces, you multiply by this. And that's what I've done. This is kind of like the conjugate, just super extra more complicated. but it is basically the same logic behind the conjugate. And so this is what I multiply top and bottom by. And after multiplication, top and bottom, by this thing, the numerator turns into this, which, if you consistently plugged in all the expressions and did the right job, you'd have x to the 1/3 cubed, which is just x. You'd have x minus h to the 1/3 cubed, which is just x minus h. So that's what the numerator turns into. And then clearly, the x and the minus x cancel each other, and the negative h and the negative, or sorry, the negative and the negative h, the negatives cancel, so that you're just left with h on top. The h here cancels with the h down here, and you're just left with the denominator. Now, at that point, you can this is continuous at that point, so you can plug in 0 for h. And when you do, you get x to the 2/3 plus x to the 2/3, right? If you combine the exponents, plus x to the 2/3, that's 3x to the 2/3. And this is indeed the derivative. That was admittedly an extremely hard one, but so it goes.